What did we discuss last class? We talked about linear dynamical systems. What did we talk about? Well, before that, we talked about dynamical systems like this, and dynamical systems are systems with memory, okay? And then we talked about linear and systems. What are these? Yeah, satisfies. Okay. Mhm. Delayed input gives you delayed output. And if something that satisfies both of these, we say it's LTI. And then, yeah, we talked about the state of a dynamical system. What is the state of a dynamical system? Sorry, what? Okay, all right. State is essentially any uh, info that allows us to compute output given the input to the system. Right? Another way to think about this is state also is associated with the memory of the system. It's usually variables associated with energy storage elements. Okay, so if we know, let's say x is the state of a system, if we know the value of state at time t naught, and we know the input for time in t naught, then with this information, we can compute y of t, the output of the system for t naught, provided we know the dynamics of the system, how the state and input affect the output. Okay, all right. So this gives us the state space formulation. What is the state space formulation for a general nonlinear system and multi-input, multi-output? We're not going to restrict ourselves only to single input, single output. So, the general, for any nonlinear system, it's like this, and your output is a vector. If you are dealing with an LTI system, then what do you have? So this is a state equation. Equation, okay, and then if it's LTI, then you have AX, where your output is. Okay. What if this was linear time variant? How this will show? Yeah, so what you'd have is simply x dot will be equal to a of t, x of t, and similarly here. That's the only difference. Okay. And then sorry, right, that's fine. Yeah. What is this? Right, this is simply how does the state of the system evolve if there is no input. Okay. And for a linear time invariant system, if the initial state of the system is x of 0, and we know this, and there is no, the input to the system is 0 from time t equals 0, then the state at any given time t is given by e power a. This is a matrix expansion. This is a matrix, n cross n matrix. Okay. Then, we talked about what is e power p a. This is simply a e square e cubed by 3 factorial e cubed, so on and so forth. And because of the Cayley-Hamilton theorem, you actually don't have to compute all the infinite terms in this series. You only need I to a power n minus 1. Okay. Uh, and then we also say if a is legible, then what? Then what is the e power the a? And let's say if a is diagonalizable, then we can write it as, then what will this be equal to? So this will simply be v e power t lambda v inverse. And what is e power t lambda? It's simply a diagonal matrix with what are lambda 1, lambda 2? Okay. If A is not diagonalizable, if A you can only get it in the Jordan form, then this will have this won't be a diagonal matrix anymore. Okay. So this is the case, right? That's where we stop. And we also said uh, lambda 1, lambda 2, and these are complex numbers. And these are also now the poles of the LTI system. Right? Now, if that is the case, let's say we say the columns of V are V1, Vn. Okay. Let V inverse, let me write it like this. Ah, we, we write it as W. I've expressed V as a block row where V1, V2 are columns, and I've expressed this as a block column, that W1 tilde transpose and so on and so forth are rows. If that is the case, now if you this expression here will essentially become so then e power p a will simply be uh, what will you get if you multiply this out? Test of your understanding of matrix multiplication. What will we get? This is a diagonal matrix. Yeah, good. Into what? Well, that's a scalar, right? E power t lambda 1 for a given value of t is a scalar. Uh-huh. Okay. Why? Why will it be that? Right. But it's a matrix though. So how does that particular scalar come out? Okay. Let's do it step by step. Let's either reduce this or reduce this first and then move on. If you, which one do you want to reduce? This one or this one? This one, okay. What will you get if you multiply this with that? So, sorry. So, so this one remains the same. Okay. This is a block column. This is the n cross n matrix. If you multiply these two, what will you get? Okay. You're saying you'll get another block column, is it? All right. And if you multiply this whole thing out, hey, hold on. Will you get a scalar? This is a matrix. This is an n cross n matrix. Is this a column vector or is it a block column vector? Right? So you cannot get a scalar, no? Because this is not a scalar and this is not a scalar. So, but if you multiply these two, what will you get? Well, this is a scalar. So, okay, you get V1. Well, that's a scalar that can come out. What is this? Outer product. That's right. What is the size of the matrix that comes out? N cross n. So it's no problem. Everything is an n cross n matrix. Summation of n cross n, you get n cross n. This is your e power ta, right? Now, that is e power ta, and your zero input response. If your zero input response is x of t equals e power ta x of 0, then I'll simply replace this with this, which is essentially, I'll change it to a summation onto n e power t lambda I di. Yeah. See, this thing here is this matrix here, or let me explain it this way. See, what this tells me, right? The zero order, the reason I did all this is to essentially to get here. The zero order response or zero input response, sorry, not zero order response. The zero input response of a linear time invariant system. If you look at it this way, if you compute this matrix, it looks complicated. Okay, you'd have a bunch of e power t terms multiplied by some scalars. It'll be mixed up. But if you re-express it like this, what this tells you is now this whole thing is an n cross 1 vector. Okay, because this is the n cross n matrix. This is the vector. This is your initial state. So this is some uh, this is some n cross 1 vector in Rn. Okay, so and what this summation tells us is your zero input response is simply a sum of a bunch of n cross 1 vectors, n of those, okay, each of which whose magnitude is essentially determined by an exponential term. So if uh, this is Rn, okay, let's say this is your x of 0. Okay? Now, uh, if you simply track, let's say, the tip of the vector x, the state vector, with at different points in time, maybe it has a trajectory like this. I don't know. I'm just drawing an arbitrary trajectory. This arbitrary trajectory uh, can be thought of as the sum of uh, the trajectories of n vectors, each of which has is either growing exponentially, determined by lambda I, decaying exponentially, or it's staying whose length is staying constant, right? And and the way you get that is what you're doing here is you're essentially finding out the component of your original state vector in terms of your eigenvector basis. Okay, so if these are your eigenvectors, that this is v1, this is v2, this is v3, this is v4, because here this is a scalar, this is an inner product, it's a scalar multiplied by vi. That means you're essentially expressing your zero input response as some scaled versions of your eigenvectors whose amplitude is determined by the exponential of the eigenvalues. So once you start it off, you find the corresponding components along the eigenvectors, right? And then from that point on, V1 might be exponentially growing or decaying. V2 might be exponentially growing or decaying, determined by the sign of the real part of lambda I. And the sum of all these vectors essentially gives you this graph. Okay, that's the idea. And another way to think about this is ax. This was your original equation. Now, if you re-express this in terms of its diagonalization, in terms of its eigenvector, right? Now, this is essentially the representation of the state vector in the eigenvector basis. Okay, let me call it, let's say, not y, z. Okay, v is invertible, v inverse exists. So if I multiply both sides by v inverse, I get v inverse x dot. This is nothing but and when you have a diagonal matrix like this, what does a diagonal matrix represent? If you have a diagonal matrix, it simply means that the set of equations that you have are decoupled. That means z1 dot only depends on z1. z2 dot only depends on z2. So in a sense, if A can be diagonalized, your original system, where the evolution of the first state was determined by x1, x2, x3, xn. If you look at the system in the eigenvector basis, then evolution of the first state vector only depends on the first state vector, and so on and so forth. That's why when you re-express it in terms of the eigenvector, in terms of the projection of your state in the eigenvector basis, your individual components simply grow or decay exponentially or stay the same. Okay, that's the idea. Okay, so with this, we'll finally talk about the last topic, which is on stability. stability of an LTI systems. Okay. Do you remember stability from your signals and systems? What what was it called? Right. What is Bebo stability? Right. There. So in signals and systems, we never worried about what was inside. Right. We were always interested in just the input and the output. So we were only interested in, well, if I give a bounded input, do I get a bounded output? Now with the state space representation, we are talking about something inside the states. Right. So it turns out there is, in addition to Bebo stability, there is another stability that we can talk about, which is called the internal stability. Which is simply the stability of the state when you apply zero input. So what happens to the state when you apply zero input? Right? And you say that LTI system is internally stable. And remember, for internal stability, the input is zero. Okay? You say an LTI system is internally stable if you start with the finite initial state. Okay? And from time t equals 0, if the length or the norm of the state, for now let's say 2 norm of the state is less than or equal to some d, that d is a positive real number. Okay, if this is true for all t greater than or equal to 0, then you say that the system is stable. That means if let's say this was your initial state, okay, and then we observe the trajectory of the state. If that trajectory is bounded by a hypersphere of radius d, that's what that means, right? If the trajectory is always within a sphere of finite radius, then you say the system is stable. If you have a system where you cannot find the sphere that will contain the trajectory, that means if you have a system whose initial state is here, and the trajectory keeps growing out, keeps expanding, and you can never, whatever sphere I propose, at some point the trajectory crosses the sphere. Then, if this is not satisfied, then you say the system is stable, is unstable. So it essentially has to do with, does my state vector grow with respect to time, or does it stay uh, uh, or does it not grow with time? Okay. So if it does not grow, that means you can find a large enough sphere that will contain the entire trajectory for all time. If you cannot find such a trajectory, then you say it's not stable. Now, so this is for stability. So then you say the system is stable. You say the system is asymptotically stable. If this is satisfied, if the and if you look at what happens to the trajectory as time increases, if the trajectory slowly winds down towards the origin, then you say the system is asymptotically stable. Okay, this is, for example, if it's just stable, if it's not asymptotically stable, then that would be a system that oscillates. It does not come to the origin, it does not grow, it just oscillating around the origin. If it slowly, either oscillates down or slowly moves towards the origin, as time increases, then you say it's asymptotically stable. If neither these are satisfied, and if you cannot bound it by a sphere of finite radius, then it's unstable. Okay. Now it should be fairly easy to see how these would be related to this. if you say that if you want to have a system which is asymptotically stable, then these terms that you have here should have a negative real value. If they have a negative real value, then you essentially have, so each of these terms would be of this form, minus 3t. Well, you could also have uh, um, a complex term. For now, we'll not worry about the complex term. If you have, if your lambda I has a negative real part, then this term tends to 0 as time increases, right? If all your lambda i's have a negative real value, each of these exponential term tends towards 0. That means whatever the original magnitude was of this vector, see, remember this is a fixed vector, right? This is a fixed vector, this is fixed, this is fixed. Your initial state value is fixed. So this is some fixed vector. If with time this term decays, that means you're guaranteed that eventually x of t will tend to 0. Okay? Because each of these scalar values goes to 0. Okay? So for asymptotic stability, all eigenvalues must have negative real parts. So whenever you have an LTI system whose eigenvalues, all eigenvalues have negative real parts, then you have an asymptotically stable system. On the other hand, a system that is stable would be one where uh, there is at least one eigenvalue with a zero real part. Okay, and another important condition is you will have uh, eigenvalues with zero real part. If there is only one eigenvalue with the zero real part, then there is no problem. But if there are multiple ones, then the eigenvalues with the zero real part must satisfy this. And what is this? Am equals A. What does it mean? Equal to? No, hold on. Every distinct eigenvalue has a distinct eigenvector. But what does this mean? When you have repeated eigenvalues, what does Am mean? Well, if an eigenvalue is not repeated, what is Am? If it occurs only once, okay? If all eigenvalues are unique, then what is Am for all the eigenvalues? One. It occurs only once. And whenever you have Am equals 1, Gm will always be equal to 1. You can always find an eigenvector. But if it's repeated, then what is Am? Well, it's a number of times that. And what is Gm? Well, the number of eigenvectors that you can find for that particular eigenvalue, right? So for stability, for just stability, not asymptotic stability, if you have, so at least one real part has a zero. One of the eigenvalues has a zero real part. And you have a stable system only when Am equals Gm. When you have eigenvalues with zero real part and Am is less than Gm, then it turns out you have a system that will blow. So it will not be stable. I mean, if that's not clear, remember what happens when you have um, repeated poles at 0. Okay, all right, that's all I wanted to say. You can basically follow a similar line of argument for the discrete time systems. So it should be clear from the slides. If it's not clear, then let me know and we can, I'll clarify whatever is not clear from the slides. Okay, so we'll stop here. That's the end of linear dynamical systems module. We can now discuss any questions you guys have for the midterm. Or if you have any questions about this, we'll discuss that now. Otherwise, we will move on. So we need to show that this is equal to. Okay, I'm going to try. I don't know if I'll get to the answer. We will try. See, the first one, if you have a plus b, if you take b out, right? Or no, let's do it this way. Um, let's write it like this. I can write it like this, right? B inverse is I. Now, if I take b out, then I get, right? But I can write this as A inverse. What do I want? I want a plus b, so I'll write it as a. Well, I need to A is on the right hand side. That means I have to write it like this if I want to take a out. So you get, yeah, that's right. That'll be a. Now I have an inverse here, inverse here, inverse here, inverse here. That means this would be equal to the whole thing, a inverse. If I multiply this side by a, okay, side by b, so this is open. So the last one is open. This you can show. Now we have to show this one. Well, you start with this and then do the same thing. You let's do this way. Let's do inverse b, b inverse plus a inverse a, b inverse. Okay, I can take a inverse outside on this side, b inverse outside on this side. So I have inverse. So I'll have b plus a. Is that okay? If I take the whole inverse of this, then b will come to this side. B inverse of inverse, that's b. A plus b inverse. That's all. Yeah. I mean, these are just a few tricks that you need to learn to be able to manipulate this. Okay. Anything else?
Subspace is also nice.
Oh, okay. Okay. So let's say we have a parent space W, and we've got two subspaces U1, U2. This is a vector space. What does it mean to say U1 and U2 are subspaces of W? Well, it's a subset of W, and it's a vector space. That means that both of these are closed under scalar multiplication and vector addition. All right. Now, what is the definition of The sum of two subspaces. What is it? Yeah. What is the definition of the sum of two subspaces? Sorry. So this will also be a set, but what is it? What set is it? What elements does it have? Yeah. What is it? Well, let's say it's some vector x. It's vectors of this form x plus y. X belongs to u1. It's simply the sum of all possible vectors from u1 and u2. Okay. And what do you have to show that this is a subspace of W? How would you show that this is a is this a subset of W? Yes, because these two are subsets of W. W is closed under vector addition. That means all these elements would be in W. That means this is a subset. But is this a subspace? Yeah, okay. How would you verify that? That means if I take any element from here and I scale it, the question is, will that be in this? Okay. If I take x plus y and I scale it, I get alpha x plus alpha y. Does this belong in? So I know that this belongs to u1 plus u2. Now, does this belong to u1 plus u2? Why? Why does it belong to u1, u2? Sorry, it's of the same what? No, that's not the, no, that's not the argument. Sorry, why? I mean, that's what I'm asking. Just because you scale it, here, all we know is elements of U1 are closed under um, scalar multiplication and vector addition. Elements of U2 are closed under scalar multiplication and vector addition. And only thing we know is U2 is simply the sum of all possible elements from U1 with all possible elements from U2. You have to now show that one of each, this is either in U1 or U2, and this is either in U1 or U2. If that is the case, their sum has to be here because this contains the sum of all possible elements from U1 and U2. Is this in U1? Alpha times x? Well, I know x is from U1, y is from U2. My question is alpha times x in U1? Yes, because it's closed on scalar multiplication. So this is in U1, this is in U2. Well, I'm taking an element from U1, adding it to an element from U2. That is by definition in the sum of U1 plus two subspaces. Okay, so at least this seems to be closed under scalar multiplication. Now, if I take x1 plus y1, this is one element from here, and I take another element, which is, let's say, x2 plus y2. This is from, well, now is the sum of, this is from here, this is another element from here. If I add those two, is this in here? It is. If you simply shift things around, this is simply the sum of x1 plus x2 plus y1 plus y2. Well, this is in u1, this is in u2. That means this has to be in. So this is also closed under addition. So it's a subspace. Okay, here is a question for you. If you have a skew symmetric matrix A is skew symmetric. What does skew symmetric mean? Not symmetric, skew symmetric. See, if you have a skew symmetric matrix, can you show that this is 0? How will you show that it's 0? Well, let's say we don't know whether this is 0. This is some alpha, some real number, right? Assuming all of this is from Rn and this is from Rn cross n. We need to show that this alpha is actually equal to 0. If this is alpha, what is this? Sorry, what? Minus what? Minus alpha, is it? Why is it minus alpha? Right, because A transpose is minus A because this is skew symmetric. So this is equal to minus X transpose X. That's the clue. So why would that mean that this is 0? Well, what would happen if you take the transpose of this? I mean, is X transpose AX equals its transpose? My question is X transpose AX equals? It is because it's a scalar, no? That is the clue. So if you take this, then you get this. If you take the transpose, what will happen if you take the transpose? No, no. Well, if you take the transpose inside, how will this change? This will be X transpose, A transpose, X transpose transpose, which is nothing but X. What is this? If X transpose AX equals minus X transpose AX, that's the only way these two are equal is if alpha is 0. Okay? This essentially means, so what does this tell me though? Geometrically, what does a skew symmetric matrix do to a vector? X transpose AX is 0, always. Is the question clear? X transpose AX is 0 for a skew symmetric matrix. I'm asking you, what does it mean geometrically? No, no. Okay, I should be more clear. When I say what does it mean geometrically, I'm essentially asking what is happening here? What transformation does A perform on X? So if this is my X, where is AX? Yeah. Hold on, it cannot be the same, no? Because if AX is X, then you get X transpose X, which is not 0. Well, we are assuming X is not equal to 0 here. Yeah, exactly. AX is what? Well, this is some vector. If X, the inner product of a vector with another vector is 0, that means the two vectors are orthogonal to each other. That means AX must be orthogonal. Well, we cannot say anything about the length of the new vector, but we know one thing for sure. Whenever you have a skew symmetric matrix, if you post multiply it by a vector, the new vector that comes out will always be orthogonal to the original vector X. So A transpose X will always be orthogonal to X if A transpose equals minus A. Okay. Eh, Okay. And now here is another interesting fact. Whenever you have a skew symmetric matrix, that A transpose equals minus A, the eigenvalues of such will always be purely imaginary eigenvalues. Okay. You could also have zero eigenvalues, but imaginary eigenvalues. And if you encounter skew symmetric matrices like this in a linear dynamical system, these are examples of systems which oscillate. Uh, for example, if you have an LC oscillator, and if you express it in this form, what you will get is eigenvalues that are purely imaginary. Yeah. Uh-huh. Yeah. Okay. Second norm. Okay. You tell me. So if this is equal, then the square is also equal. That's the clue. If the squares are equal, what is the second norm? Square of the second norm of a vector.
So
No, vector. We're not talking about x and y are not scalars. You are right, but you have to express it in the matrix form or in the vector form. How is the square of the second norm? I mean, square of the second norm of a vector is related to another concept that we saw, the inner product. How is it related to the standard inner product? That's the clue. So you can now, so if you express both of these as what? So you can express this as transpose minus y. What will this be? So you can take the transpose inside. If you do it, you'll get x transpose x plus y transpose y minus 2 times x transpose y. Okay. If you do the same thing for this side, okay, then you'll get the same thing, x transpose x, y transpose y plus 2 times. If these two are equal, then, well, this is equal to this, that means this is gone. You are left with minus 2 times x transpose y equals 2 times x transpose y, which means 4 times x transpose y equals 0. That means x and y are orthogonal. That is what I've written, no? Oh, what will it look like? What will the vectors look like? Well, all we know from this is x and y are orthogonal to each other. That means if this is my x, this is my y, right? Y is orthogonal to x. What is x plus y now? Where will be x plus y? Where? Here is it. Well, the parallelogram law of addition, that's here. This will be x plus y. This is the origin. What about x minus y? Sorry, where? How will you find out x minus y? Hey, no projection, nothing. If, no, you'll have to tell me where it is. You should not make any guess. How will you find x minus y? Yeah, where is it? Here is it? Here? This side? Ah, exactly. See, x minus y is simply the sum of x and minus y. What is minus y? Minus y is this. The sum of x, this is minus y. The sum of x with minus y is x minus y. This is x minus y, right? Okay. Essentially, these two will be the diagonals of your rectangle. That's all. It's This is essentially a restatement of the fact that if you have a rectangle, the length of the two diagonals is the same. If you have a parallelogram, then x plus y is greater than x minus y. Yeah, that's the geometry. That the length of the diagonals of a rectangle are equal. Why is it the diagonal? This is the main diagonal. If you move this up, this is the other diagonal. That's not clear why x minus y is the other diagonal, because if you move this up, it's here. Okay. What does it mean? Okay, I'll take this one. Okay. If you have, if you're talking about some mapping from R to R3, and if you're talking about a linear map, then that linear map is represented by what? Can be represented by a matrix of what size? If it's a map from R2 to R3. Are you sure or are you guessing? 3 cross 2, yes. Because what goes in here, the only thing you can multiply on this side is a 2 cross 1 vector. If you're talking about multiplying a vector, what comes out is a 3 cross 1 vector. Okay, what is the question? See, I don't know what more to say. A mapping from a set of two numbers, two real numbers, to a set of three real numbers is given by matrix A. What specifically are you looking for? I don't know what else to discuss. If you tell me specifically what is it that what you show me the question, then I'll I yes. Yeah. The question was, there is a linear transformation f from R2 to R3. Okay. So if you take a vector from R2 and pass it to this linear transformation f, you get a vector y, which is in R3. And then what you know is, well, we know that this linear transformation f can be represented by a 3 cross 2 matrix, but we don't know what matrix, right? But what we know is this: if you take the vector 2, 0, and you apply this function f, you get 2, 4, minus 2. And if you take the vector 0, minus 1, and you apply this function f, you get minus 1, 0, 1. Now the question is, with just these two pieces of information, can we find out the matrix A? That's the question, right? Okay, we'll give it that. Okay, see the clues here. If 2, 0 gives me 2, 4 minus 2, what would 1, 0 give me? Because I know F is a linear map. If 2, 0 gives me 2, 4 minus 2, what will 1, 0 give me? Why? Because, well, half times this should give me half times this because F is linear. So I would get 1, 2 minus 1. Okay. Similarly, if 0 minus 1 gives me this, what will 0, 1 give me? Yeah, 1, 0. That's all. Right. So now my matrix would simply be 1, 2 minus 1, 0. Sorry, 1, 0, and so this is my matrix. Why is this my matrix? I don't know. I mean, I could have written anything else here, right? Why is it that I have a 3 cross 2 matrix? The first column is given by the input 1, 0. The second column is given by the input 0, 1. Well, let's verify. I'm saying this is a matrix. Let's verify at least if those two are satisfied. What will happen if I multiply this by 2, 0? What will I get? What will I get if I'm... Are you sure it will be 2, 4 minus 2? You're not convinced? Yeah, see, if it's not clear, just multiply it out. Just blindly apply the rules of multiplication. Yeah, he needs to be convinced. So, right? Okay, so that is, so at least for this input, this mapping seems to be correct with this matrix. What about 0 minus 1? If this was 0 minus 1, it'll come, right? Okay. Now I ask you, what will happen if you input some arbitrary alpha beta? What will be the output of this function? So if I do f of, what will I get out? Well, scale how? Scaled version of what? Here. If it's not clear, here. I can express alpha beta like this. Alpha 0 plus 0 beta. This is okay. Since f is linear, I can move the f inside the parentheses. That means I can simply write this as f of this plus f of this. That's clear? Okay. That's again because of linearity. What is the output of the system for any vector alpha 0? Well, I know if I apply 1, 0, I get 1, 2 minus 1. That means if I apply alpha 0, I get alpha 2 alpha minus alpha. So the output for this, so alpha 0 would give me alpha 2 alpha minus alpha. What about 0 beta? Well, 0, 1 gives me 1, 0 minus 1. That means this should give me this beta. And if I simply add these two together, that will simply be f of alpha beta. So that means if I apply alpha beta, what I get is alpha plus beta 2 alpha 2 alpha minus alpha Okay, this is purely from what we know, that f is linear and that we know that this map produces these two outputs. Okay, we do not appeal to this matrix. Now what will happen if you do this? Will you get the same output? You can verify that in fact you will get the same output. That means this is in fact a representation of your f. That means if this is what you need to know. If you have a linear map from Rm to Rn, this can be represented by a matrix of what size? N cross M. If you have access to this function f, how would you find the matrix A? Let's say there is a Python function that you can call. Okay, you simply call f with whatever vector you want, and then it'll give you this. If you give x from Rm, it'll give you a vector in Rn. Let's say I want you to find out the matrix A that represents f. How will you find out? I mean, there are many ways to find out. Tell me one way to find out. Yeah, okay, all right. If you simply pass to f of x, pass to the function f, the m unit vectors from Rn are m, will that be okay? Here, f I'm saying is equivalent to the matrix A. I want to know the elements of matrix A, right? If I um, pass on E1 to the function f, what will I get out? Well, I'm saying f of x equals ax. I'm saying what will happen if I pass E1? What will I get when I multiply A by E1? First what? Hey, hold on, not the first element. What you get is a vector. Yeah, exactly. If you pass in E1, you will get the first column of A. If I pass in I pass in E1 to F, the Rn vector I get, I'll simply take that and put it in the first column. And then I put E2, whatever I get, this. So if I call that function m times, each time with E1, E2, E3, E4 to EM, the outputs that I get, if I simply stack them into a matrix, this is my matrix A. Okay? That is exactly what we did here. We did not have the input as E1, but it was a scaled version of E1, and the second input was a scaled version of E2. And if we know the output for E1 and E2, we know the matrix. Okay? The same logic applies for a linear function. I said any linear function with, well, linear functions are we said any linear function f of x can be represented like this, where W is from Rn. The question is, how do you find W? You do the same thing. If you pass E1, what will you get? So if I compute f of E1, what will I get as my output? If I do, hey, this is a vector. Sorry, is the question clear? Yes. We said here, if you have a linear function that maps from Rn to R, if f is a linear function, then it can always be written like this. That means you can identify a vector W such that W transpose x will be exactly equal to f of x for any x that you choose. If you had access to f of x, my question is, how would you find out W? The equivalent representation of f in terms of a single vector. Okay, all right. We'll do the same thing. What will happen if you multiply by E1? What will you get? Hey, first column, is it? W itself is just a column. What is W? Is simply W1, W2, Wn. Yes, this will give me W1. If I pass E2, Em or En, I'll get Wn. That's all. I mean, it's just a generalization here, except instead of this being, let's say Rm, M, this is M, this is N is equal to 1. That's all. Anything else? Yeah.
It's not mine. Just for the question.
Uh-huh. Okay, so you have uh, vector u, that's in Rn. Well, let's say we're talking about R2. So this is u. This is the subspace spanned by u. The question is, what what is it? What is the geometric operation performed? So if you have a matrix, well, what is this matrix first of all? Let's say you, okay, what is this matrix? Yeah, right. This is orthogonal projection matrix. The question here is, what does this matrix do? Okay, so that means if you take this and then you multiply it by some vector v, you get some w. The question is, what is the w? Okay. Well, I mean, you simply go through, you take v, so this, if you take it inside, this will be v, this will be 2 times u, u transpose, u. We know what this is, right? So if, let's say this is, I won't draw u anymore. This is the span of u. See, this is v. What can we say about this vector? Yeah, geometrically, where is the vector? U transpose by u transpose u into v. No, no, no. Span of v is all this line, this entire line. My question is simple. Where is u transpose by u transpose u? You agree this is a matrix, right? This is a matrix. If I multiply it by a vector, I get a vector. I'm asking you, where is this vector? Right. You drop, Nicola, and this. Well, I have fancy chalk, so we can use that. Yeah. So this is your u. Well, I'm going to call it uv or v u. Okay. Okay. But what we want is this. We don't want vu. We want u v minus 2 times What do we do now? Well, 2 times uv, that's here. This is 2 times, sorry. Okay. That's this. But we have to find out v minus 2 times vu. How do we find that out? Yeah, okay. Okay, you flip this. That'll be here. This is minus 2 times vu. Now what? Okay, we add. So and then this line. This. So the vector. Yeah, I'm going to roughly draw. This will be my v minus 2 times. What do you think is happening geometrically, roughly? This is the clue. Ah, exactly. Who said that? Yeah, reflection. So this operation here, I minus 2 times some projection matrix, essentially gives you the reflection of the vector u v about what? Where is the mirror? The mirror is not along u. Where is the mirror? Yeah, exactly. The mirror is along the orthogonal complement of u. Okay. So this is the orthogonal. Say this is R2. So the orthogonal complement is of size 1. But if you were dealing with R3, this would be a plane, and then you would find the corresponding reflection on the other side of this two-dimensional orthogonal complement. Okay, so this is a matrix that reflects vectors. Okay. Okay. All right. If there are no other questions, we'll stop here and we'll meet on Friday.